I just want to clear up. There was a few calculation errors, and nothing could be solved quite quickly. So instead of what was written here, it was evaluated that this was 36 plus 36 minus a 104 over 3, which gives us 72 minus 104 over 3, and the final answer is 112 over 3. So that's the value that we have when we integrate um, the double integrals in this order. Now let's look at the reverse order. And what the good thing about the reverse order is that it allows us to check if our answer is correct. And in doing so, we can see that both answers will be the same if the integral is correct. So now, still the same problem, but we're gonna reverse the order in which we do the integral, but also want to take a look at right here. If we were to look at this region that we spoke about, when we reverse the order, essentially what are we doing? Well, remember I kept on speaking about, well, we're going to rewrite this and we're going to hold one of the integrals constant. What this translates into when looking at the graph is we were holding, in this example, where we're holding the x term constant. That's if we're holding the x term constant, what will be the y? What would be the y in terms of y to create this region? So if we are to do the reverse, we hold the y terms constant. So this would now be your limits, your respective limits with holding the dy or the y terms constant. So we will be holding this region or this axis constant and evaluating for the x term, and still within the region. And that's what it means graphically when we are reversing the order. But numerically, we shall still have the same volume, the same integral. So let's go back to that. So we left here, and the value was 112 over 3, and we'll just go back when we finish the reverse order, calculations for the reverse order, and check to see if our answers are correct. Okay, let's rewrite that equation in reversed order. So before, like I said, we held the x term constant. Now we're going to hold the y terms constant. So in reverse order, we have the limits from 1 to 5, and dy is held constant at 2 to 3, and our f of x, well, before it was the f of y, now our f of x is x squared plus y, and in respect to x. So again, we're solving for this portion right here. So in terms of x, the x squared, we'll rewrite again the constant integral from 1 to 5 dy. Okay, evaluating here, x cubed over 3 plus a xy. The limits are from 2 to 3. We write the constant. And plug it in the limits for the x term. So x cubed is 3x cubed over 3 plus 3y all to be minus by 2 cubed over 3 plus 2y, and the limits are from 2 to 3. Sorry, those were the limits that we just plugged in, so let's just erase that. I'm quickly just going to simplify this. Rewrite the constant. 1 to 5. Integral from 1 to 5 dy. And the simplified form of that is 19 over 3 plus 1, or y. We could have just simply put the dy at the back for conventional purposes. Easier to look at. Okay, and now we're going to integrate with respect to y. Okay, so if we are to integrate with respect to y, that 19 over 3, this is simply 19 over 3y plus a y squared over 2 from 1 to 5. So we have 5 times 5 times 19 is 95 over 3. 95 over 3, 5 squared is 25 over 2, minus a, we're putting in the lower limits for the y value, which is 1, 19 over 3 plus a 1 over 2. That gives us 76 over 3 plus 12, and finally that works out to be 112 over 3. And now we can see, as suspected, that, well, we are correct because the two values are the same. Okay, so that's problem 1 of the first tutorial. I'll see you in the next recording.